Hi there. In this video, we're going to talk about conformal mapping. So conformal mapping is actually a very important application of complex analysis. What people use it for is that they take extremely difficult geometries with very complex shapes and whatnot, and they transform it using transformation equations into shapes that look much easier but preserve some of the essential information about the original shape. For example, if you look at the wing or the airfoil on an airplane, you can see that it's of a certain shape, and if you were to investigate the fluid mechanics of that shape, you would see that the boundary conditions of the differential equations are actually influenced by the shape. So what we can do is that we can transform some of these shapes in many different fields of engineering to be able to analyze the information and obtain simpler equations by doing some transformation or mapping between the different complex planes. So there's a reason why we need to check if a mapping or a transformation between different planes obeys what's called a conformal restriction, rather not a restriction, but rather a kind of condition in which some information is preserved. And we can start off by looking at lines. So we have our normal Z plane with the X and Y coordinates, and we have two lines. That's A, B, and then maybe AC here. If a mapping from the Z plane to the W plane is said to be conformal, then what we need to ensure is that the angles between these transformations is the same. So between AB and AC, there's an angle alpha, and now this is mapped into the W plane with its coordinate systems being U and V, and now we have A prime here, and then we have B prime here, and then we have C prime. So now these angles must also be the same here. So the angle there should be alpha. So the reason for this is, even though we may transform geometries into a complex shape into a simple shape, we want some essential information like angles to be the same. So for a transformation to be conformal, then what it has to ensure is that the angle, in this case alpha, is the same in both the W and Z planes. It's also important to note that the angle should be in the same direction. So the direction is also important. So the angle is in the same direction. So in this case here, it was measured counterclockwise. We can see we measured alpha to be counterclockwise from AB to AC, and the same is the case here as well. So if we want to now extend this to curves, you can see again we have our Z plane with X and Y, and our W plane. We have the W plane here with U and V. So what we need to check are the tangents. So we have some intersecting points. Okay, we have a tangent associated with the one curve. So let's call that C1, and we have another curve C2, and that curve will also have a tangent. So it would look something like that. So we can call this maybe tangent 1, and we can call this tangent 2. So if we now look at the transformation, then what information needs to be preserved is also in terms of the tangents. So we'll have maybe call this tangent 1 prime, and we can call that tangent 2 prime. So the tangents here will have a certain angle. We can call that alpha as well. So in the case with curves, this angle alpha should also be the same in both instances. So for curves, we just need to check the angle alpha between these different curves in the transformation and ensure that they are the same. So what we also associate with tangents is the derivative. Okay, so if we're saying that the angle should be the same, what happens if the derivative is equal to 0? What happens now if we have tangents that are equal to 0? So there's the one tangent like that, and there's maybe another tangent like that. So both of these tangents are 0. So does that mean anything? They are technically parallel to each other and the angle between them is 0. So does that mean anything? So the answer to that is that no, it doesn't mean anything. If the derivative, that is f prime z, is equal to 0, then what this means is that it's not conformal. So if we are checking if a certain mapping is conformal, then we also have to check f prime z and ensure that this is the case. We could have a certain function of z, for example, z is equal to 1. So this is actually a circle. So that's a circle. Because you're talking about the magnitude of z, that's x plus minus j, right, equal to 1. Unit circle. Now we can have a transformation, w is equal to z plus 4 over z. So that's our transformation now. So the question is this mapping conformal? How would we do that? Well, the first thing that we need to see is that there is one particular point where z is not defined, and that's where z is equal to 0. We can see that if we substitute 0 in here, we have an undefined value of w. So when we have that undefined value, that we would call a singularity. So we have a singularity at z is equal to 0 because it produces an undefined value of w. So now we can also check critical points. Remember that earlier we spoke about we need to check f prime z is equal to 0. So that indicates critical points. So we have to check critical points. So all we need to do is simply find dw dz. And this function is analytic everywhere except for z is equal to 0. So we find the derivative. We find that it is 1 minus 4 over z squared. And if we set this equal to 0, then we find that z is equal to plus minus 2. So this would be the critical points. So what we are saying here that the function is conformal, right? This is a conformal mapping except at plus minus 2. So it's conformal except for everywhere besides the critical points. So this particular type of transformation forms part of what is actually called the Joukowsky Transformation. So what this is that it takes a circle, a unit circle, as we had shown earlier, z is equal to 1. Okay, that's roughly like a circle, unit circle. And what it produces is this z plus 4 over z. So if we were to actually plot this out or determine analytically what the shape looks like, we find that it's actually a ellipse. Something like that. So we made a circle into an ellipse. So with a little bit more work, a little bit more manipulation of this transformation equation, we can actually play around with this shape a bit more and make this shape a bit different. Maybe something like that. The point is that we can make this shape more and more look like the wing of an airplane or an airfoil. So this is how this kind of mapping or transformation is actually applied. And we find that it actually works besides the points plus minus 2. So the key takeaway from this video is that conformal mappings are quite important because we can use it to represent a great deal of different geometries and make them simpler to work with. But the key thing here is that we have to check that the angle between lines geometries are the same. And also we have to ensure that when it comes to curves, we have to check for singularities and critical points. So thank you very much for watching.